welcome to the Deep Dives. So we are jumping into a fascinating stack of sources today, all focused on the work of the American physicist Edward M. Purcell.
Right.
And this isn't just a biography. The mission here really is to see how Purcell learned to, listen, to listen to the hidden motion inside everything.
That's it, exactly. And the sources frame his big discoveries. We're talking nuclear magnetic resonance, the 21-centimeter line, things like that, all through this very specific lens they call motion theory.
And that's our analytical tool for this deep dive.
Yeah.
This isn't your standard physics textbook. We have to adopt this new vocabulary to really get what the sources are saying.
We do. Before we get into any discoveries, we have to reset some basic definitions, starting with the biggest one, motion.
Okay.
In this theory, motion isn't what things do, it's what everything fundamentally is.
So nothing is static. It's all just patterns of movement. So then what's an object? Like a proton or, I don't know, this table?
It's just a long-lived, stable pattern of structured motion, a rhythm that holds itself together.
Got it. And a concept like a magnetic field, which is central to Purcell's work.
The sources define that as a motion gradient. It basically describes how motion is encouraged or resisted in a certain area of space.
Okay, that vocabulary helps. So the mission is clear. Purcell's career shows that if you're clever enough, you can actually hear these patterns. So let's start with his huge 1946 breakthrough, NMR.
Nuclear magnetic resonance. I mean, the standard story is already great, right? Purcell and his team figure out how to measure atomic nuclei absorbing and then re-emitting radio waves inside a magnet.
But with our motion theory lens, it's more than that. So instead of a nucleus being a tiny spinning ball, what are we looking at?
You should think of it as a tiny, tightly bound motion loop that has its own internal circulation.
And because of that circulation, it has a magnetic moment. It's like a tiny compass needle.
Exactly. And Purcell's experiment starts by putting these motion loops, in his case, the protons in water or paraffin wax, into a huge, powerful motion gradient, the big static magnet, the B field.
And they don't just snap into alignment, do they? There's another layer to it.
No, they precess, they wobble, just like a spinning top that's been tilted.
The gyroscope analogy.
Right. And the speed of that wobble, that's its native rhythm in that specific field. We call it omega naught. And the beautiful thing is, it's perfectly predictable. The stronger the field B, the faster the rhythm.
The sources kept mentioning this conversion factor, gamma. Why is that so important?
Because that's the signature. The gyromagnetic ratio, gamma, is unique to each type of nucleus. Hydrogen's gamma is different from carbon-13's. It's the key that let Purcell know exactly what rhythm he needed to listen for. He could calculate it in advance.
So how did he actually hear it? I mean, the energy involved must have been incredibly tiny.
It was. His brilliant move was to hit the system with another motion pattern, a radio wave. At exactly that native rhythm, that's resonance.
Like pushing a kid on a swing at just the right time.
Precisely. The motion loops absorb that energy, they get kicked into a higher energy state, and then as they relax back down, they release that energy. They re-emit it, and that's the signal Purcell's machine picked up.
He's basically feeding a pattern of motion an energy snack at its favorite beat, and he gets an echo back. But then comes the real magic, the thing that turns this from a physics trick into an essential tool, the chemical shift.
Yes. This is the profound part. He found the resonance lines were super narrow, which meant the spins had amazing coherence. They were all wobbling in perfect sync. But then he realized the exact frequency wasn't just set by his big magnet.
It was based on the neighbors.
Exactly. The local environment, the electrons buzzing around, the nearby atoms, they all create their own tiny fields that slightly shield or enhance the main B field. And that tiny change shifts the native rhythm.
So in our motion theory language, what is the chemical shift actually a map of?
It's a map of motion retuning costs. Each local environment, each chemical bond, slightly retunes the natural wobble of that proton. NMR is literally a spectrum of how much it costs to make that motion pattern change its tune.
And that has, just massive consequences. Let's connect it directly for the listener to medicine, to MRI.
The power of an MRI scan comes entirely from this. When a doctor looks at your scan, they're not seeing atoms. They're mapping the retuning costs of hydrogen nuclei all over your body.
So the hydrogen in water in, say, healthy tissue behaves differently than the hydrogen in a tumor.
Because it's in a different motion environment. It has a different chemical shift. Its retuning cost is different. That's how you can tell soft tissues apart. You weren't seeing stuff. You're reading a map of hidden synchronized motion.
That's a perfect transition. We've gone from the spatial map, the where, to the temporal one, the when. We're moving from frequency to how long the signal actually lasts.
Yeah.
Section 2, coherence decay.
Right, the physics of relaxation. This is where you get into the thermodynamics of it all. Purcell's experiments didn't just find the signal, they let us measure precisely how that signal decays. And that brings us to T1 and T2.
Okay, let's break those two down. What is T1?
T1 is the spin-lattice relaxation time. It's a measure of how quickly the ordered energy you just pumped into the spins gets dumped into the chaotic motion of the surrounding environment, the lattice.
So it's energy leaving the spin system and turning into heat, basically.
It's essentially, yes. It's order becoming disorder.
Then what's T2?
T2 is spin-spin relaxation. It's different. It measures how quickly the spins lose their synchronicity, their coherence. They start to dephase, to fall out of step with each other because of tiny local variations in the field.
And they can lose their synchronicity before they even lose the energy.
Exactly. T2 is always shorter than T1. The shared rhythm breaks down faster than the energy actually leaks away.
So for motion theory, why is this T1, T2 distinction so important?
Because it's a perfect benchtop model for how coherence decays into randomness. You are literally watching a highly synchronized, structured motion pattern bleed out into chaos second by second.
And you're drawing a line from that process to something much bigger.
The sources do, yeah. They see it as a...
Okay, so the mechanism here. You have a hydrogen atom, one proton, one electron. Both have spin.
Right. And those two spins can either be parallel, pointing the same way, which is a slightly higher energy state, or anti-parallel, which is the lower energy ground state. When it flips from parallel to anti-parallel, it spits out a photon.
And that photon has a very specific wavelength, 21 centimeters.
Or a frequency of about 1420 megahertz. In our motion theory view, this whole atom is a compound motion loop, and that 21 centimeter photon is the exact little motion packet that gets released when the loop retunes itself to its most stable configuration.
The incredible thing is that the whole galaxy is just full of neutral hydrogen doing this all the time. It creates this faint, constant radio glow.
And that glow became maybe the most important tool in radio astronomy, because you're not just seeing where the hydrogen is. By using the Doppler shift, you can tell how fast that hydrogen is moving.
So you can measure the speed of giant gas clouds.
You can map the rotation of the entire Milky Way. You can find the spiral arms. And crucially, this is how we first gained concrete evidence for dark matter. The hydrogen on the edges of galaxies was moving way too fast for the amount of visible stuff there. Something else, something invisible, had to be providing the gravity.
You're mapping the universe by listening to the motion of its most basic part.
It's the ultimate scaling up of the NMR principle. And what's wild is that this spin flip is technically forbidden. It's incredibly slow.
How slow?
The average hydrogen atom only does this once every 11 million years or so.
Wow.
But there's so much hydrogen that, over cosmic scales, this tiny probability becomes this huge measurable signal. It just confirms that the universe is the sea of structured motion, constantly returning itself.
Purcell really was the master of finding the natural rhythms of a system, wasn't he?
He was. And we should quickly mention the third piece of the puzzle, the Purcell effect. It sort of ties it all together.
This one is maybe less famous, but it's foundational for quantum optics, right?
Absolutely. What Purcell showed is that even so-called spontaneous emission isn't truly spontaneous. The rate at which an excited atom gives off a photon depends entirely on its environment.
So in our lingo,
it means the rate at which a high-energy motion pattern can relax depends on how the surrounding space, the electromagnetic vacuum, is allowed to vibrate. If you put that atom in a tiny cavity tuned to its frequency, you can make it emit much faster. You're encouraging the motion.
So we can actually engineer the local environment to control the rate of a fundamental physical process.
That's it. You're manipulating the motion gradient of space itself to change the lifetime of an excited state.
So when you put it all together, from the nucleus to the galaxy, the lesson from Purcell is this mastery of rhythm. He showed that if you learn the native frequencies of a system, you don't just observe the universe.
You can actively listen to it doing spectroscopy on itself.
He taught us how to tune in, how to see that every structure is just a story about coherence holding out against randomness.
Which brings us back full circle to coherence decay, to T1 and T2. So if we take that benchtop model seriously, that synchronized motion inevitably decays into random heat, and that this might mirror the universe at large, here's the thought to leave you with. How does that model challenge or reinforce our understanding of the ultimate fate of all the synchronized patterns in the cosmos? Is everything destined to fall out of tune?